Hi, welcome back to my channel. Well, in this video we'll try to learn some of the basic concepts of probability, which plays a very important role, rather a vital role in decision making and data driven decisions. So let us proceed. If an experiment is repeated under essentially homogeneous and similar conditions, we generally come across to two types of situation. The first one is the results, or what is usually known as outcome, is unique or certain. Such kind of situations are known as deterministic. So we can exactly predict the outcome with certainty or accurately. The result in another situation, the result is not unique but may be one of the several possible outcomes. Such situations are known as probabilistic. The example of deterministic approach is if we want to accurately calculate the velocity of a particle, then if we are aware about its initial velocity, its acceleration and time, we can accurately get the velocity of that particle. So this type of situations are known as deterministic. There is no uncertainty, so we can get the results or the outcomes which are certain and quite unique. But there is another situation. In tossing of a coin, we are not sure whether head will pop up or tail will pop up. So such kind of situations are known as probabilistic situations. For example, the possibly it will rain tonight. This year the demand for the products is likely to exceed. The odds are 3:2 in favor of getting the contract. There is a high chance of getting my appointment this month. These words like possibly, likely, odds and chance, these are some of the expressions which are an index of uncertainty. So we need a certain kind of measures or certain kind of numerical expression which can measure the different grades of this kind of uncertainty. So a numerical expression or a numerical measure of uncertainty is provided by a very important branch of statistics, which is known as theory of probability. Moving ahead, by looking at a clear sky, one will say that there will not be any rain today. On the other hand, by looking at the cloudy sky or overcast sky, one will say that there will be rain today. In the earlier sentence, we aim at there will not be rain, and in later we expect rain. But in terms of statistical language, or we can say in the language of statistician, a statistician says that the probability of rain is 0 in the first statement and the probability of rain is 1 in the second statement. Hence, it is important to develop a firm understanding of what exactly the probability means. So, probability is a measure or a number used to measure the chance of occurrence of some event. In ordinary language, the word probable means likely or chance. Generally, the word probability is used to denote the happening of a certain event and is likelihood of occurrence of that event based on the past experience. This probability actually lies within the range of 0 to 1, or in terms of proportions, we can say the proportion of times an event may be expected to occur if an infinitely large number of trials are made. Then, since everything is revolved around the chance, and in probability we always use to measure the degree of chance, or we use to measure different gates of uncertainty which range from 0 to 1. So this chance is how likely it is that something will happen. To state a chance, we use a percent. 0 means certain not to happen, or 1 means it is certain to happen, and 1/2, or we can say the 50% chance, is equally likely to happening or not happening of an event. So before moving ahead, there are some of the important definitions that we need to look at. The first one is experiment. An experiment is some procedure or a process that we do, or we can say a well-defined operation or a trial under controlled conditions. Sample space. The sample space of an experiment is a set of all possible outcomes of an experiment. Also, it is called the universal set and is denoted by this symbol. Another important definition is trial and event. An experiment which, though repeated under essentially identical or same conditions, does not give unique results but may result in any one of the several possible outcomes. Therefore, performing an experiment is known as trial, and the outcomes of that experiment are known as events. Now, we used to have different types of events in probability, and one of the best examples to explain these kinds of events is either tossing a coin or rolling a die, because in coin we have only two outcomes. One is head and another one is tail, and in die we used to have 6 dots or 6 faces, which range from 1 to 6. So we will start with the exhaustive events. The exhaustive events are the total number of possible outcomes in any trial is known as exhaustive events or exhaustive cases. Take an example of a coin where this 2 raised power n is nothing. 2 determines head and tail because we have 2 faces in coin, and n determines the number. So if we toss a coin once, that means the total number of exhaustive events in case of tossing a single coin is 2 raised power 1, that is 2. And if we toss it twice, then 2 raised power 2 is 4. So the number of exhaustive events in case of tossing of 2 coins is 2 raised power 2 is 4. In case of a die, if we roll a single die, it is 6 raised power n, and if we roll it twice, it becomes 6 raised power 2, that is 36. So there is another important event that is known as favorable event. The number of cases favorable to an event in a trial, or the number of outcomes which entail the happening of event. And another important definition is mutually exclusive events. Events are said to be mutually exclusive or incompatible if the happening of any one of the event excludes or precludes the happening of all other events. That is, if no 2 or more of the events can happen simultaneously in the same trial, the joint occurrence is not possible. Take the example of a coin. If we toss a coin, if head will come up, then at no circumstances the tail will pop up. And same is the case with die. If we roll a die and we will get 2 dots, there is no possibility of rest of the dots like 1, 3, 4, 5 and 6. So rest of the dots will not appear. That is known as mutually exclusive. Equally likely is there is no preference. If that means head and tail both are equally likely. In rolling of a die, the dot 1 up to 6, they are all equally likely. So equally likely events are like the outcomes of a trial are said to be equally likely if taking into consideration all relevant evidence. There is no reason to expect one in preference to others. So there is no preference, like in the case of example of a tossing of a coin. That is, 2 or more events are said to be equally likely if each one of them has an equal chance of occurring. And there are another 2 important definitions, that is independent event and dependent event. So independent events, as far as independent events are concerned, there are several events are said to be independent if the happening of an event is not affected by the happening of another event or one of more events. Now, as far as dependent events are concerned, if happening of one event is affected by the happening of another. So we can take the example of coin and die into consideration, then easily we can interpret each and every event. We will start with the number of exhaustive events, favorable events, mutually exclusive and equally likely. Then classical probability. This is the basic definition of probability. So in terms of classical probability, if an experiment results in n exhaustive cases which are mutually exclusive and are equally likely cases, out of which m events are favorable to the happening of an event, then the probability p of happening of A is given by this. So the probability, it is nothing, it is the ratio of these two. So this is the favorable events, and n is the total number of mutually exclusive or equally likely exhaustive events, where m is always greater than or equal to 0 and n is also greater than or equal to 0, and both these m and n, these are positive integers. So you will always expect that the range of probability will always lie into 0 to 1. So the probability is a non-negative real number and cannot exceed unity. It always lies in the range of 0 to 1. So in this case, the probability of not happening of an event A is denoted as like this, and the probability of happening of an event is not like B, and if it is not happening, it is denoted by Q. For example, two dice are tossed. What is the probability of getting? The situation first is sum 6 and sum 9. So the solution is, when two dice are tossed, the exhaustive number of cases is 36, which is quite simple. 6 raised power n, that is 6 raised power 2. Therefore the sum is 1, 5, that is 1, 5, 2, 4, 3, 3, because we have to get the sum of 6. So 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. Therefore the number of favorable cases is 5, 1, 2, 3, 4 and 5. So that is 5 upon 36. And if there are 9, then we have to do it in the similar way. Only we will get 1, 2, 3 and 4. In this case, that is 4 upon 36, 1 upon 9. So in first we will get 1 upon 5 upon 36, and in second we will get 1 upon 9. This is very simple. Then there are some general probability rules. The probability lies in the range of 0 to 1. The probability of a sure event is always equal to 1, or a certain event, and a probability of a null event or uncertain is always equal to 0, and the probability of not happening of an event is always denoted as 1 minus the probability of happening of an event. Now there are some important rules. So we will start with the first one. The probability computations basically follow either addition or multiplication rules. When we have two events and we are interested in knowing the probability that at least one event in which we are interested occurs, we use the addition rule. Another way of stating this rule is, if we are interested in knowing the probability that an event A or event B or both occurs, we simply add the elementary probabilities. When applying addition rule, it is important to know if we have mutually exclusive events or not. Let us take an example of a plant breeder who in a single experiment on chlorophyll transformation gets a yellow colored seedling instead of green one. He is faced with mutually exclusive event. Here the equation for addition rule may be stated as follows. Probability of A or B, or we can write it as probability of event A plus probability of event B, or probability of A union B is equal to probability of A plus probability of B. The above probability statement is read as that the probability that either A or B, this is very important, A or B will occur is equal to the sum of the probability of A and B, which is nothing. This is the interpretation of this statement. For example, if we roll a single die, the probability of getting a 2 or a 3 would be, so we can write in this, the probability of 2 or 3 is equal to probability of 2 plus probability of 3, like in this equation, or we can write it like this. Since we know the probability of a single event, single dot in case of a die is 1 upon 6, so probability of getting 2 is 1 upon 6, probability getting of 3 is also 1 upon 6, so it's 2 upon 6, so 2 upon 6 is nothing, it is 1 upon 3. Further, it is also possible for both events to occur, so addition rule to such occurrence is when events are not mutually exclusive. Here the events are mutually exclusive, and there is another situation, if the events are not mutually exclusive, then this whole expression can be written it like this. Then we can write it at probability of A plus probability of B minus probability of A and B. Then on the other hand, if we are interested in finding the probability of two or more events occurring simultaneously, we are applying multiplication rule. This rule is applied differently depending upon whether we are dealing with the events that are dependent on or independent of each other. Two events are statistically independent of each other if the occurrence of one in no way affects the probability of the second occurring, or we can say the second event occurring. For example, assume we have a pair of dice, black and white. The appearance of 3 on white is completely independent of appearance of 3 on black. Here in multiplication rule, like we have stated previously in addition rule, we used to write probability of A or B is equal to probability of A multiplied by probability of B, or we can write it probability of A intersection B, because in addition we used to write a union here. Then instead of addition we used to apply here a multiplication symbol. Using this condition, we can determine the probability of throwing a 3 with a die, as the probability of 3 on white and 3 on black is probability of 3 on white multiplied by probability of 3 on black, like this equation says us. That is equal to 1 upon 6 into 1 upon 6. It is nothing, it is 1 upon 36. Now, when two events A and B are dependent on each other, the probability of occurrence of one event is dependent or conditional, which is a very important term, on occurrence or non-occurrence of other event. So the notation this, which means given, this notation is a very important notation and plays a very important role as far as the conditional probability is concerned, as far as the Bayes theorem is concerned, which means given is used to indicate the conditional nature of a probability statement. For example, probability A given B is read as the probability of an event given the condition that event B has occurred. Multiplication rule is based on conditional probability. So probability of A intersection B is nothing. It is equal to probability of A into probability of A given B, or we can write it like that: probability of A intersection B is equal to probability of B into probability of B given A. So we can write in both ways. So this notation is very important. Now the conditional probability. The conditional probability, or we can say the probability of occurrence of one event given that another related event has occurred, is known as conditional probability. The equation given below, this one, is the way in which a conditional probability of two events A and B is noted mathematically or statistically. Or we can say probability of A given B, we can write it like this: probability of A intersection B upon probability of B, or we can write it vice versa, like probability of B given this A has already occurred. Here in this condition the event B has already occurred, and in this condition probability this A event has already occurred. For example, in a class of 100 students, there are 60 boys and 40 girls. 16 girls and 9 boys, they wear eyeglasses, and if we select at random we are selecting from the class, what is the probability that a student wear eyeglass given that she's a girl or he's a boy? So the solution is, let S be the event for the student, B be the event that a student is a boy, G be the event that a student is a girl, and E be the event that a student uses eyeglass. So S is nothing, it is the total number of students, that is B. Then the probability of boy is 60 upon 100, and the probability of the girl is nothing, it is 40 upon 100. Then this E intersection B is 9, and obviously the E intersection G is 16. Then the probability of E intersection B is 9 upon 100, and in case of this it's 16. Now if we use a definition of a conditional probability, we can simply write the probability of E upon G. E stands for the eyeglass and G stands for the girl, so we can apply this formula here. Then obviously it is 16 upon 100 and whole divided by 40 upon 100, and we will get 2 by 5 in case of the first case, and that she's a boy, it has got a probability of she's a girl, 2 by 5, and in case of the second one, that the student is a boy and he wears eyeglass, that is 3 upon 2. This is very simple. You can pause this video here and you can easily understand what this actually be, because simply you have to substitute these values in this the formula of the equation of this conditional probability. Then there is an important concept of inverse probability also, where current and past events are taken into consideration, or it is a blend of current and past events in nutshell, I can say. That is known as Bayes probability, and he has given a very important theorem that is known as Bayes theorem. Bayes probability is also known as inverse probability. The idea of inverse probability was given by Sir Thomas Bayes in 1763, which was reprinted in a very famous journal, Biometrica. This K is a very significant figure because this was actually Biometrica CA, and due to the contribution of the Carl Pearson, this C was converted to K. So this is a very important significance of this K here. In 1958, the problem of inverse probability arises when we have an outcome and we want to know the probability of its belonging to a specified trial or the population out of many alternative trials or population. So here we have mutually exclusive events on a collection of events, each belong to a subset of a sample space. So in Bayes approach, we used to find out the probability of an event given that another event has already occurred. So it's based on the conditional probability. So by means of this example, will make you understand. Imagine a farmer who is deciding whether to water their crops. The farmer knows that when it's cloudy, there is 80% chance that crops will need watering. In the form of probability, we can write it like this. And when it is sunny, there is 30% chance the crop will need watering. So in the form of this, it is probability of watering given there is a sunny day. So historically it is cloudy 40% at the time of this is a given condition. Now the farmer wants to know the probability that the crop needs watering given that it is cloudy. So if we take into the consideration of Bayes theorem and this the concept of this conditional probability, so we will write let A be the event that crop needs watering and B be the event that it is cloudy. So the probability of B upon A is 0.80. That is the probability it is cloudy given that the crop needs watering, and the probability of A is nothing, it is the probability of watering given the cloudy multiplied by the probability of cloudy plus the probability of watering or sunny. So this is the probability of sunny, that is 0.4%, or cloudy 0.4%, and simply we can calculate this probability of A and probability of A here. Then the overall value is 1. So the probability that the crop needs watering given that it is cloudy is 1 or 100%. In this specified example, if it is cloudy, the farmer can be certain that the crops needs watering based on historical data. Although this looks quite a difficult one, but to make you understand, let us go to the another slide, and in a common layman's language I will try to explain it. Imagine this is the same example, instead of using this calculation, or because sometimes the students who are from agriculture or forestry background, they used to they have a different kind of thinking about this subject, because when the equation or some mathematical term pops up in front of a paper or in front of a slide, so it becomes a bit scary. So make it more simple and to make you understand the concept of this Bayes theorem utilizing the previous example, let us take this example again. Imagine a farmer has two fields, field A and B. The farmer knows historically that when it's cloudy, field A requires 80% of watering, and while the crop in field B needs only 30%. So he knows from historically that A requires more watering and B requires less watering. Now let us say it is cloudy today. Without going into the calculation, we can say that based on the historical data, there is higher likely that the crops in the field A needed watering compared to for B because of its cloudy. That is similar to the idea behind Bayes' theorem in agriculture. The probability of an event that crop needs watering given certain conditions, cloudy weather in this case, is influenced by the historical probabilities of the event occurring under those conditions in different scenarios, field A and B. So in simple terms, Bayes' theorem helps farmers to make decisions by considering past, which I have said in the previous slide, past data, and adjusting their expectations based on the current conditions. So if historical data shows that the crop in a specific situation usually needs watering, the farmer is more likely to make decisions like irrigating the fields when those conditions are present. So it is a joint consideration of the present and the past future. So usually the doctors used to give the prescription. They used to, if the patient goes to a doctor, then whatever the patient goes to the doctor, what doctor does, he used to see his past history. He used to see his or her past prescription, what kind of medicine he is using, what kind of medicine he is using, or what kind of disease he was having, and based on that past and the present condition of the patient, the doctor writes the prescription. The same is the case with this Bayes theorem. Now there is an important concept in probability that is known as principle of counting. because in some experiment the sample space is so large that the total number of outcomes in an experiment is very complex and difficult to determine. In such situations, it is helpful to understand some counting principles. Such principles are used in cases for more than 2 events, and two important, or we can say the famous principles of counting are permutation and combination. They are widely used. As far as this permutation is concerned, the formula is here NPR, where NPR is read as the number of permutations of n things taken r time, and in case of combination we used to have this kind of NCR, where NCR stands the number of computations or combinations of n things taken given this r factorial. Well, n factorial here, it stands for the factorial, or we can say it's a multiplication of n natural numbers upon n minus r factorial, and here we have this extra r factorial. So if an outcome excludes repetition but order is still important, in such outcome we are dealing with permutation. We may define permutation as an arrangement of a set of objects in which there is first, second, a third and n order. While as far as this combination is concerned, in this the order is not important, so we use combination principle in grouping the things. So in nutshell, we can say permutations are used when order or sequence of the arrangement is needed. So order is very important in permutation, but in combinations are used to find the numbers of possible groups which can be formed. So here the combinations we used to have the number of groups which can be formed. Here the order is not important, but in case of permutation the order is very important. Let us take into consideration the two simple examples. So how many permutations of letters Y, L and S can be obtained by taking 2 letters at a time? So the clear thing is here n is 3 and 2 it stands for r. So in case of permutation we will write NPR is equal to n factorial upon n minus r factorial. Then in terms of this we will simply write 3 factorial upon 3 minus 2. 3 minus 2 is 1. So here this is nothing, 3 into 2 into 1, because this is a factorial term. Then 3 into 2 is 6. So 6 divided by 1 is always equal to the number of permutations in case of this example is 6. So taking the same example into consideration, how many combinations of letters Y, L and S can be obtained by taking 2 letters at the same time? So in case of combination we will write NCR n upon r factorial, n into multiply by n minus r. Then in terms of factorial notation we will write 3 factorial upon 2 factorial, then 3 minus 2 implying the BODMAS rule. Here we will write 3 factorial upon 2 factorial, because 3 minus 2 here is 1. Then 3 into 2 into 1 divide by 2, that is 3 multiplied by 2 is 6 upon 2. So 6 divided by 2 is 3. So in case of combination we have got a value of 3, and in case of permutations we have got 6. So in case of permutation the order is very important, but in combinations we don't need any kind of. So these are the two important principles of counting which can be used in probability. So the concept of probability is very important as far as the decision making is concerned, as far as the data driven decisions is concerned. So probability is nothing, we can say it is a measure of occurrence of chance, or the proportion of times an event may be expected to occur if an infinitely large number of trials are made whenever we are going to take a certain kind of decisions, and it plays a very important role as far as the probability distributions are concerned. So hope you will like this video. So in next video we'll try to learn and explain some of the important probability distributions. Thank you very much.